And like when you work this out in abstract algebra 2, you prove this makes sense. This is the sort of thing that I probably will actually do in number theory if we don't get too many fellow travelers. Actually, so if there gets to be, if the class gets big enough that I can't do this, I'll do this with you on the side.
Okay.
Yeah.
Have more people signed up for it?
I can check. So this works out to what? Well, this works out to AC plus, BDX squared plus AD plus BC times X plus this ideal J, right? But what's the deal with X squared?
I mean, it's still just real numbers. Oh, what's to do with X squared?
X squared for the representative is minus 1.
Yeah.
So you see what you have here is you got AC minus BD plus AD plus BC times X plus the ideal, right?
Yeah, which is the same thing, just collapse it all down.
Right. So the product of A plus BXJ and C plus DXJ is AC minus BD plus AD minus BC X plus J, right? So, in other words, drop the J, think of it formally, and what you have
is your generator.
A plus BX
Plus the generator.
times C plus DX equals to, AC minus BD plus X times AD plus BC. So, where what? Where X squared is minus 1, right?
Yep.
What is that? What is this product? I mean, this is exactly the complex numbers.
Yeah.
Complex numbers. So complex numbers can be formed by real polynomials mod the quotient generated by X squared plus 1.
So
This is a way of constructing the complex numbers as a quotient of a polynomial ring.
Okay. Wait, but R of X are functions, right?
Well, you could look at them as functions, but I just look at them as polynomials. Polynomials don't have to be looked at as functions, they can be looked at as expressions.
Okay.
Meaning that we're not actually we're not thinking of them as having a domain and a codomain, we're just thinking of them as a finite sum with powers of X, where X is thought of as quote-unquote an indeterminate, which is just a fancy way of saying we're not insisting to think of them as functions.
Okay.
Which really means that if you could find a contradiction to their existence in terms of the function evaluation not making sense, we don't care about that.
Okay.
That's really what it means. But anyway, yes, these are complex numbers. So how would you make the hyperbolic numbers in this wild new way of...
X squared plus 1 equals 1.
You want X squared equal to 1, right?
So you minus 1.
You put a minus 1 here, that's the... Straight up, that's the hyperbolic numbers.
Yeah.
So to create this one, formally, you could just do
J squared, or what would J squared be the?
well, not J squared this time. J cubed.
Oh, J cubed. Okay, yeah. You'd have X cubed minus 1.
Right. Yep. Yep.
Wait, can you? No.
Now, if you're thinking X cubed minus 1 factors, and that should mean things, you're absolutely right.
Okay.
Indeedly doodly.
Okay.
In the same way, listen, it's like, so in abstract algebra 2, one of the big theorems we learned later on is that if you quotient by an irreducible polynomial, an ideal generated by an irreducible polynomial, then that ends up giving you what's called a maximal ideal, and a ring mod a maximal ideal. It gives you a field. So this is a maximal ideal, in fact, because this is being generated by an irreducible polynomial, and that's why this is a field. In contrast, this is not a field, because this polynomial is not irreducible. In fact, it factors. Yeah.
Yeah.
And so, yeah, it's not a field. Likewise, when we look at hyperbolic numbers, if you want to think about them as a polynomial ring, quotient of a polynomial ring x squared minus 1, well, again, this factors.
Yeah,
and so
x
it's,
squared minus, or x plus 1, x minus 1.
right. And so it's not irreducible.
Yeah.
Now,
But when it is irreducible, what did we say again?
the quotient gives you a field.
Oh, okay.
So if this is irreducible, the ideal which it generates is maximal. And then the quotient of a ring by a maximal ideal is a field. This is something we'll prove. I think we'll prove these particular we prove these particular aspects of abstract algebra in the number theory course, independent of who shows up there, because it's in Stillwell, and it's part of the main thoroughfare of that course. It fits. Anyway, what's interesting? Remember last time we proved that we found an isomorphism of the hyperbolic numbers in the direct product algebra. It's not an accident. It's not an accident at all that this was isomorphic to R cross R, direct product algebra. Incidentally, if you take the real polynomials and you mod by the ideal generated by x plus or minus 1, just one or the other of them, it's just R again.
Yeah.
Because in this ideal, either x is equal to 1 or minus 1.
Yeah.
So the polynomial is just in the polynomials representing an ideal collapse down to the constant. So you've got constant plus ideal, which is isomorphic to just the constant. I mean, this is essentially the reals. So this you could look at is sort of R of x mod x plus 1 direct sum of R of x mod x minus 1. That's not an accident. Like when you're dividing by something that factors, it ends up giving you something which is like the direct product of the quotients by the separate factors.
Yeah. So we could rewrite that. So
there's some nuance to there. We'll add an abstract algebra too, but yeah.
So we could rewrite that to be like R across the quotient with x squared plus 1, or x squared plus x plus 1.
Oh, this one?
Yeah.
Yes. It's isomorphic to that at least.
Okay.
And this is irreducible.
Okay, so that means that's its own field.
Indeed. So this is actually x plus 1/2 squared plus 3/4, which is irreducible, which makes modding by that. Essentially in this weird algebra, if you set that equal to 0, that makes x equal to like minus 1/2 plus or minus, I times the square root of 3 over 2 essentially. If you want me to talk about it in terms of, well, that's not the way to say it. I mean, this is what's 0, right? So it doesn't make x like I, it makes x kind of like that. So
Yeah.
yeah.
Well, you could reconstruct the complex numbers,
But-
get a lot of them.
But yes, this is in fact isomorphic to the real numbers, direct sum, the complex numbers. That is true. And it is not disconnected from the reality of that factorization that we just revealed. Alright, now I've told you all kinds of complicated,
Yeah, I had to stop writing it to figure out.
fancy stuff, but what I actually came here to show you in this example was the regular representation of this thing. But you have righteously distracted me by talking about why does this thing even exist.
No, but it makes sense.
But I will show you another explanation
Okay.
of why it exists. In fact, this was the easiest explanation that I should have given you to start with. Well, I don't know. I have a love of polynomial of quotients because they are really, really simple. If you can just step aside from the abstraction of it and just look at it's just so clean.
Yeah. Clean things are nice.
But assume for a moment, though, that it exists. In other words, that you have, you know, oh man, this one instead. So, you know, we have a plus bj plus cj squared times x plus jy plus zj squared, right?
Yeah.
And you multiply them like normal, all right? So I'll work it out. That's a, how's it go here? Ax, jj squared, so plus bz, and then j squared j plus cy, and then the j terms, you got yourself ay plus bx plus cz, because j squared times j squared is j, as you told me.
Mm-hmm.
And then plus, that's all times j, right? And then the j squared terms, we got ourselves, of course, az plus by plus cx, j squared. So there you go. I mean, you could, this is essentially the definition. I mean, I derived the definition in terms of assuming that j cubed is 1 and proceeding normally is what I will tell students who just want to know how to do it and don't care about why, you know? But there it is, right? Now, so this actually is the formula for the left multiplication map, right? So what we're looking at here is left multiplication by a plus bj plus cj squared, right? On x plus, you know, jy plus zj squared, right? And if we say, okay, you know what, I'm just going to think of A as a point set as being R3. And I'm going to let 1 equal to E1, I'm going to let j equal to E2, and I'm going to let j squared equal to E3, as I can. All right. So with respect to that nomenclature, I have, you know, ax plus bz plus cy, ay plus bx plus cz, az plus by plus cx, all times x, y, z. Oh, excuse me. There's no times x, y, z there. That's from the future.
E1, 2, E3.
There's nothing there. It's just a column vector.
Oh.
All I've done is rewrite what's right above it and about to be underlined in orange.
Something pretty cute. Something reminds me of cross product for some reason.
Yeah, see, that's the thing that never quite worked out. Is like Hamilton was trying to find an algebra on R3 that somehow incorporated the cross product, played well with the norm on R3, and was analogous to what we see solve for complex numbers, and it can't be done. You have to go to 4 dimensions, and that gets you the quaternions, which have both the dot and the cross products at once, but...
No, but it just looks way too similar to the cross product.
Let's see here. So this, if we want to make the matrix, times x, y, z, whatever goes in that matrix is the so-called, this will be, you know, if this thing is alpha, then whatever goes over here is what we call the map, the matrix of alpha, right? The regular representation of the left multiplication map by alpha. What goes in the box?
A, B, C.
Mm-hmm.
But how? That's the better question. We need to.
So yeah, it's flippity floppity. So it's A A with X, and then C with the Y, and then B with the Z. So this dot with that gives me AX plus CY plus BZ.
Yeah. And then this one would be, the A would be in the middle, the B would be the first term, C would be the last term.
Very good.
And then I think the last one was ABC. No, A's last, so it's C, B, A.
Right. Now, let me just, so this is how I discovered the regular representations to start with. I would point out to you that because we're where we are, that M of alpha is also equal to the matrix, which has got alpha in the first one, and then alpha times the second thing, and then alpha times the third thing. And of course I don't need the times here, I can just write, we're using juxtaposition for multiplication, so I could say it's alpha, alpha j squared, right?
Mm-hmm.
Because here, the identity is the first element, so the regular representation, since we're working in Rn, it's just element times the second basis, element times the third basis. When you multiply this by j, it brings, when you multiply this by j, you get, alpha j is what? Alpha j is
AJ, B,
right, it's
BJ squared, C.
Right, it's C plus JA plus J squared B, right?
Mm-hmm.
Which is why we have this CAB over here. That's good?
Yeah.
Okay. So that's the regular representation of the what I call the three hyperbolic numbers. Which, again, is the group algebra of the cyclic group of order 3 for what it's worth, but this one here, you could have, what I was trying to say is, you could have defined this algebra in terms of the set of matrices that look like this. No one would complain, well, that doesn't exist. How do you know that even exists? If I just said, look at the set of 3 by 3 matrices of the form ACB, BAC, CBA, like that, such that A, B, C are real numbers, right? I said, there's a subset of 3 by 3 matrices. Prove it's a subalgebra of 3 by 3 matrices. People would do it, right? You can prove that, in fact, it's tedious in this kind of approach, but you can prove that the product of such things is again such a thing, that the sum of such things is again such a thing, so it in fact will be closed under addition and matrix multiplication. And the fact that it's a unital algebra is manifest from the fact that you can put B and C both 0, and you can take A equals to 1, and you get the identity matrix, right? And since it's a subset of the matrix algebra, it's associative. And since we're defining the algebra product in terms of matrix multiplication, it's got all those lovely distributive properties that we want. It is a unital algebra. And so you ask me, does it exist? I could have defined it in this way. In a similar context, if you wanted to, you could define complex numbers as 2 by 2 matrices of the form A minus B, BA. That gives you a concrete set of objects that has an object in it which squares to -1, where -1 is understood as the 2 by 2 identity matrix. So people who criticize abstract algebra in terms of that you can't do that, that doesn't even exist, they just really haven't thought much about it.
Yeah, but the quotient, the generators, clicked in my head more so than this does.
Oh yeah, I mean this is, right. But in this context, what does J look like as a matrix? What's M of J?
Okay, that would, so it'd be J, j squared and 1.
That's true. That's very good. And what's that look like? That's 0, 1, 0, 0, 0, 1, and 1, 0, 0. Which of course you can also see from coming up here and putting b equal to 1 and the other 0. But that matrix is a matrix such that if you square it, you don't get 1. But if you cube it, you get the identity matrix. This matrix is so-called Eigenvector.
Why would you set b equal to 1 in that case? Since b is the first.
Because b equals to 1 gives you j. If I put a equals to 0, c equals to 0, b equals to 1, it gives me j.
Okay.
Okay, so lovely. We've got our regular representation, so-called 3 hyperbolic numbers. Now, question. If we look at a function, right, say u plus jv plus j squared w, I'm mapping from h3 to h3. I usually call this thing h3. 3 hyperbolic numbers. What does it take for that to be h3 differentiable?
Wait, if we thought about it matrix-wise, we couldn't have a determinant 0, right?
Oh, no. I mean, I don't know about that. But for this function to be h3 differentiable, it has to have a differential, right? It has to have a differential, which we understood as a mapping from A to A, in this case h3, which is right, h3 linear, right? And remember, that means that the matrix of the differential is an element of the regular representation. In other words, what it says is that the Jacobian of this function has to be an element of the matrix representation of the algebra, right? Another way to write that would just be that there are various ways to attack this. The one way is just to look at the Jacobian directly in terms of what it means, and maybe that's actually useful for us for a second here. So df of 1, or df of j, right?
Okay.
Is df of 1 times j, which is df of 1 times j. But here's the thing. This is really df of E2 is equal to df of E1 times j. In advanced calculus, we learned that the differential of E1 or E2, these are partial derivatives.
Yeah.
So like this is partial f partial x2 equals to partial f
Partial
x1 times j.
Yeah, we did this in differential geometry, right?
I don't think so. I mean, we've talked about this stuff. Not the multiplication by j part, but the fact that df of e is the partial derivative. Yeah, we did that.
Okay.
So if I play the same game for df of j squared, that's df of 1 times j squared, right? Which is df of 1 times j squared. This gives us what? Partial f partial x3 is partial f partial x1 times j squared, right?
Yeah.
So, yeah, those are the quotient Riemann equations in vector form. We have this, and we have that. Now, what is it? Let's look at this from a slightly different angle.
And what about df of 1?
df of 1 is partial f partial x1.
Okay.
So this right here, right? This means that jf is equal to what? It's equal to, well, it's equal to the matrix representation of some number alpha, right? So it means that it's got alpha in the first spot, right? It's got alpha times j in the second column, and it's got alpha times j squared in the third column, right? In our current context, that's what the regular representation looks like. But what does the Jacobian look like? Jacobian matrix of a function look like? It looks like partial f partial x1 for the first column, partial f partial x2 for the second column, partial f partial x3 for the third column, right?
Yeah. So that's how most Jacobians look, isn't it?
If for when the x1, x2,
Yeah.
x3 are the variables in the domain, yeah. So if you just equate,
Yeah, but we could rewrite that as partial f partial x1 stays the same. Partial
So
f partial x2 you could rewrite as partial x1j.
right, so like this has to be that, right? Which then you can take and go, aha, so that's here.
Yeah, and then partial x3 is partial f x1j cubed. So you can write everything in terms of partial x1.
Right, so you pretty quickly see how that equation up there and these two down here.
Yeah.
But you gotta understand, what do these mean at the level of scalars? Keep in mind f is u plus jv plus j squared w, right? So this is 3 equations, and this is another 3 scalar equations. And you can unwrap this. This is, you know, if you don't mind, I'm going to stop using 1 and 2 and replace this with like derivative with respect to y, derivative with respect to x,
Okay.
z, and x. All right, so this gives us ux plus jvx plus j squared v, oh, y, not x, dummy. J times ux plus jvx plus j squared wx. This one gives me uz plus jvz plus j squared wz is equal to j squared times ux plus jvx plus j squared wx. So each one of these vector equations gives us 3 scalar equations, which I will now write out. I was tempted to get some 5-hour energy for you for lunch. I was thinking. So the real components, you've got ux, uy on the one side. What's the real component here? J squared times j is j cubed, right?
Yeah.
uy equals to wx. And how about the j component?
J. Wait, for which
I'll
one?
do the easy part. vy.
Oh, then so for 1 it'd be j squared w. No, sorry. It'd be j. Give me a second. Okay, so we did uy to wx because that's 1 with j squared. that would mean Vy would be equal to Ux.
Right.
And then Wy would be equal to Vx.
Right. And then similarly, reading off the J imaginary and the J squared imaginary. Am I stupid? I'm just being a dummy, but this is stupid run. We got UZ.
Yep.
Or Uzi, if you like.
And that would be Wx. No, it's squared, so it would be Uz would be equal to Vx.
Right, Vx, very good.
And then that one would be J squared. That would be Vz. J squared. Would that be Wx? No.
Oh, you might be right. Yeah, J times, yeah, you got it. Sorry, I was just still processing.
And then J squared would be Ux.
Process elimination.
No, yeah.
Right? But you're
for
right.
the last one, yeah. No, I was.
But you're right.
Yeah, how I'm thinking about it is like not dividing, but I don't know why this makes sense to like you multiplying it on the other side. Is how I'm getting these things, and you want to match up what equals to each other.
Mm-hmm.
Because Ux would be equal to V. Would be equal to Uy Wx. That would equal 1 because you're pushing 1. Vy Ux would be J. Oh, never mind. That would make more sense. J. That'd be 1 now. I'm still thinking here.
So the other way, the way I did it at the start of all this, when I first learned this stuff, is I would find the pattern that it had to follow.
Yeah.
Then I would set that pattern equal to the arbitrary Jacobi matrix, Jacobian matrix, and then just pattern match, so like A gives us Ux equal to Vy and Vx equal to Wz, which is like this one. And that's in here somewhere. I don't know where this last one. I mean, for what it's worth, you can see this one and that one is coming from A, matching A in this equation up here. It's like A is being equal. A equals A gives you those two. And like B equals B. So B is here and here, so that makes like UZ equal to Vx. I think it's this one.
Oh. No, I don't know if I'm wrong, but if you divide, like, I might just be going crazy here, but if you took J, if you look at the equation, you took J and divided it, the number before it is how you would match it up, right? I might be going crazy, but we'll see.
Maybe. Sorry, I think I've written something wrong here.
Maybe. J1.
Huh. Actually, I think this one is C equals to C, and I think this one's also from A. So I have Vx equals to, sorry, I've got Ux equals to Vy, Vx, oh, that was the V. Vx,
J
V.
squared Ui.
This one is Wx. Oh, this one's not A, that one's C.
No, yeah.
So this one and this one, they're both C. I don't know.
This is how I'm doing. Like if you were, this is really weird, but like if you were to divide this J
Uh-huh.
and like divide it on this side by each term, if you divided J by 1, you get J squared,
Uh-huh.
which matches that. If you divide it by J, you get 1, then by is ux. If you divide it by J squared, you get J, and wy is equal to dx. And I think the same thing is true here.
There are a lot of patterns that appear in this example that don't appear elsewhere.
Yeah, so I'm just trying to see if it works for these two cases. J1 divided by J squared would be J squared J uz. No, that's 1. Vx. No, yeah, that'd be J. J squared divided by J squared would be 1 J squared. Oops. J squared. So BZ Wx, yeah. J squared divided by J squared would be 1. And then Wz is Ux. Don't know if that means anything, but that's how I was matching them up.
But, I mean, my original approach was I just basically multiplied the J through in my head and equated coefficients of J in 1 and J squared.
Yeah.
Okay, but, you know, this is the color, the coloring pattern that's often used for like children's toys.
ACB.
Like they'll use a blue, red, green.
Interesting.
If you look at like little 9-button phones, they'll use this color scheme. I have to give credit where credit is due. This is common due to Spencer and I. Yeah, so these are the 3 hyperbolic numbers. So what are the zero divisors in here? So just counting, by the way, there are 6 Cauchy-Riemann equations.
Yeah.
Which makes sense because this is a 3-dimensional algebra.
N squared.
And so like 9 minus 3 gives you 6. You need 6 equations to fix a particular kind of matrix in a 9-dimensional space of matrices.
Okay, so you said we're looking for zero divisors now?
Yeah, we can do that. Now, what I said in our, what I told you is to find the zero divisors, all we gotta do is take the determinant of a regular representation of an arbitrary algebra element, set it equal to 0, and go to town on that. So we got it right here. All we gotta do is take, the determinant of the regular representation of alpha is the determinant of A, C, B, B, A, C, C, B, A. Just gotta calculate that thing, right?
Yeah.
So we've got A times A squared minus BC minus C times AB minus C squared plus B times B squared minus AC, which gives us A cubed plus C cubed plus B cubed minus thrice ABC.
So equals 0?
Yeah, well that's just the determinant. So if this is non-zero,
Yeah.
it's a invertible element of 3 hyperbolic numbers. And if it's 0,
So yeah.
then it's a zero divisor.
1.
Can you factor this?
I was just telling you the matrix, the 1 would be a 0. ACB equal to 1.
Yes, very good, all ones. So you're like a plus b, 1 plus j squared is a zero divisor. Very good. I have a notation, let me use it then. Ooh, very nice, very nice.
Wait. No, that'd be 27. Wait, I also think for some reason 1/3.
What if you tried like could you do like,
I think 1/3 would work.
well, of course we know -1 minus j squared in there.
Yeah.
So check this out. So this, we have min to thank for. Although I think Spencer claimed to have found it too. I don't know, Min and Spencer were funny, they get, you're like, I found that, and Spencer's like, I found it too. A little bit. But anyway. So you're forced to put an a squared here.
Yeah.
And you're forced to put a b squared here.
And C.
And a c squared. Because that's the only way. When you multiply this, you can get back.
But you have the minus things that are nasty.
Right, and so now here's the trick.
There's a -3 somewhere. No,
Yeah, well the trick here is that ABC appears symmetrically. There's no difference between A and B and A and C and B and C. So whatever formula you write, it must respect this symmetry of interchange of ABC. ABC interchange symmetry. And so that essentially forces you to write minus AB, minus AC, minus BC. And so if you start multiplying stuff out, so like this gives us a minus minus a squared b, right? But then I get a plus a squared b, those cancel. And it gives me a minus, well, it gives me minus ABC, great, want that. It also gives me a minus, did I do a squared b? A squared b. But that gets, and so like these two, so these two cancel with these.
Yeah. No, the math, that part I got. I was looking for more zero divisors.
So, oh, yeah. Now,
I think 1/3 is one.
so is this guy in here, or is this guy in here? In other words, this is the consequence of which one of these factors being 0.
I would say it's a plus b plus c would be 0.
But this is a equals 1, b equals 1, c equals 1. It makes this factor 3.
No, not always. Because you don't have a, c, and b don't necessarily have to factor out that way. You could have, no, it does.
I mean,
No, yeah, it does.
this here, now I'm a little fuzzy. I don't,
No, wait. I think they can all be -1 too. That would be -3.
this gives us a, b, and c are all 1.
Yeah.
And so that's 1 plus 1 plus 1, minus 1, minus 1, minus 1. It's this factor,
Yeah.
which is 0.
Okay.
Um,
I'm trying to do honky tonky stuff. Maybe negative, so if you do negative.
Hello, Benjamin.
I think, no, well, I think all the zero divisors would be, they would be a scalar of 1, of the 1, 1, 1.
Well, I mean, either we're looking at
Well, anything that's scalar of 1, 1, 1, because negative 1, 1, 1 would also work. 1/3 would also work. I think 3, no, 3 would not work. No wait. 27. 3 times 3. No. 3 cubed. 3 cubed is 27. That'd be 52. That'd be. No. That'd be 54. That'd be. Yeah, I think it's all scalars of 1.
Daddy, I got candy.
Oh, I can't think.
I got candy.
You got candy.
Yeah, you got some candy.
61. 3 times 3 times 3 times 3. No. 27 times 3. No, yeah. 3 also works. But
3 what?
like, I'm getting all scalars of 1 for zero divisors. Like, if I haven't.
Oh, you mean like 3, 3, 3?
Yeah, 3 3 3 works.
Oh yeah, sure, absolutely. Any multiple of this
1, yeah, okay.
will work. That's true.
And then, what else? Could you have different ones?
But yeah, I mean, if we believe this, then something like 1 minus j is a zero divisor because it's got a equals to 1, b equals to minus 1, c equals to 0.
Mm.
And that makes this factor 0, and hence it makes the determinant 0, and that makes this not invertible.
Okay.
So like that's a zero divisor of a different type than this.
Yeah. Okay. So once you find. Okay.
So this factor over here, right?
Yeah.
This guy, we could write as 1, 1, 1, and then minus a half on the off diagonals. This is a real, so that piece is a quadratic form. So what I'm asking the question right now is like, what is that quadratic form? See if I can find its eigenvalues, then I can write a simplified formula for it in terms of eigencoordinates.
Never learned eigenvalues.
So this here is the symmetric matrix. By the real symmetric theorem, I can rewrite this as something like lambda 1, a bar squared plus lambda 2, b bar squared plus lambda 3, c bar squared, right?
Mm-hmm.
And depending on what the eigenvalues is, that will give me insight as to what exactly we're dealing with here. Because when I look at, if you tell me, well, what is a squared plus b squared plus c squared minus ab minus ac minus bc equal to 0 in ABC space, I don't know.
Almost looks like that one, what was it called? Trig identity.
It does look like that. How about this one though? A plus b plus c equal to 0 in ABC space. This is a
Vector? Or the origin?
this is the equation of a plane,
Oh, yeah, it is.
right? With normal 1, 1, 1. So like, yay, we got a, this is this guy. So this is part of the zero divisors of H3. Right? The question is, what is in the other thing, right? I mean, this 1, 1, 1 you just found me, that ain't in here. It is, it just so happens that you picked the normal to the plane. That's kind of cool, right? Your answer was out here somewhere. Your initial observation, that's in the zero divisors, right? That's normal to the plane. So what is that? What if you set that quadratic equal to 0, what is it? So, if we can calculate the eigenvalues to that matrix, then we're off to the races, right?
Yes.
So I'm going to just go ahead and feed it to my favorite Eigenvector Calculator, which is linked on my website, because it's been a few years since I did this. And I don't remember, it's number 4, no internet, whoa, how dare you. How dare you. I like the old version of the calculator. So the matrix we're looking at is 1 minus 1/2 minus 1/2, oops, minus 1/2, 1 minus 1/2, minus 1/2, minus 1/2, 1. Right?
Mm-hmm.
Cool. So this has, if I haven't done it wrong, it turns out to have an eigenvalue of 0 as well as 3/2. So lambda 1 equal to 0, lambda 2 equal to lambda 3 equals to 3/2. The eigenvector corresponding to eigenvalue 0 is 1, 1, 1. The eigenvector according to the other values are minus 1, 1, 0 and minus 1, 0, 1. So this formula here is straight up 3/2 b bar squared plus 3/2 c bar squared. So like ABC, it's equal to a bar times 1, 1, 1 plus b bar times minus 1, 1, 0 plus c bar times minus 1, 0, 1. That's how, well, I'm sorry, I'm missing some normalization factors here. So let me put some quotes around this, because technically I need to, well, yeah, there's some normalization factors that are a little sketchy here, but I'm kind of out of time, so sorry. The point is that if your ABC is a scalar of 1, 1, 1, and it's got nothing in here and here, in other words, b bar and c bar are equal to 0, that makes this piece 0, which makes all of this, which is that factor right there, 0. The other way you could get that to be 0 was if you had, like, another way you could get this, you could also get this to be 0 from having like a equal to b and c 0, or you could have, in this one, you could have am I saying equal to c? Sorry, second. No, that wouldn't make it 0.
No, a equal to b, it would not make it 0.
No, yeah, you're right, that wouldn't make it 0 at all.
No.
No, that's it. This is the only, actually, okay, so, yeah, I'm sorry, let me think more clearly here. The only way for this factor to be 0, since this is what the formula simplifies to an eigencoordinates, the only way for that to be 0 is if both of these eigencoordinates are 0. So we need b bar equal to 0 and c bar equal to 0. Now b bar being 0 means that a is equal to b, and c bar being 0 requires b equals to c, I believe.
So yeah, cool, B.
Is that right?
That would make sense for all of them to be 0. But isn't that just a scalar 1, 1, 1?
Well, yeah, I'm not quite. If b bar and c bar are both 0, okay, if b bar and c, if these are both 0, that implies that ABC is equal to like a bar times 1, 1, 1. From this down here. If b bar and c bar are both 0, then it makes ABC equal to a multiple of a bar times 1, 1, 1, which makes a bar equal to a equal to b equal to c.
Yeah.
Okay, but that's it. You see, that's all that can happen here. So this equation equal to 0, it doesn't give you something interesting like an ellipsoid.
Yeah.
It just gives you a line. Because it just so happens one of the eigenvalues is 0. So, yeah. So in short, the zero divisors in H3, as advertised several hours ago, is a plane and a line.
Oh yeah.
So, and that's it for H3. That's it. It's not an accident
No, that's nice.
that this is a plane and that's a line. That has very much to do with the fact that it's also isomorphic to the reals.
Mm-hmm.
Direct sum, the complexes. See, because if you look at the algebra, if you look at the algebra, let's say C direct sum R, or direct product with R,
Mm-hmm.
and so this has things of the form Z comma, A, such that Z is a complex number, right?
Mm-hmm.
In that wild world, that algebra right there, you have 1, 0 times 0, 1 equal to 0, 0.
Yeah.
So these guys are zero divisors in this algebra. Let me call it B.
Is that because you're dot producting it?
Well, in this direct product algebra, the rule is if you have like A1 direct product A2, our rule is we multiply Z1 and Z2 according to the rules in A1 and in A2 respectively. So like
0, 0.
this is 1 times 0, this is 0. This is 1 times 0 as a complex product. This is 0 times 1 as a real product. But either way, we get 0.
So it is a dot product, but kind of, but without the plus. You add a
Yes, it's a dot product without the plus. Very good. Now, these are zero divisors.
comma. Yeah. But they're also 0.
So, right, and I'm pretty sure that if you're going to construct an isomorphism from A equal to H3 to this fangled direct product algebra, that, what do you want to do? Well, the theorem we had earlier, zero divisors go to zero divisors.
Mm-hmm.
So you can kind of use that in part as a guide for how you're constructing the isomorphism. You have some sense of what's going on here. See that plane of zero divisors